straight up and then it flatline continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually.
Okay, we can see here, this is an oscilloscope. If we measure the current to the resistor, when we start it instantaneously, it rises its maximum value, that is indicated by the voltage divided by the value of the resistor, E divided by R. Okay? And it will be constant. But the inductor, the current in the inductor is not instant. It starts to push against the resistance of the inertia until it reaches its maximum value and steady state status.
Continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to zero. But when we stop the current through the inductor, the current continues and we get another curved profile.
Okay, and then if we disconnect the battery, the resistance, the current through the resistor becomes zero because there is no potential difference across it. It instantly comes to zero. But the inductor, who has been maintaining a magnetic field, this energy, it will push a current in the opposite sense, but from the maximum value to zero. But it also will take some time. So that's when it is discharging. This is the charge of the inductor and the discharge of the inductor. But it takes some time, but we will see something that is called the time constant. Hay una relación que se llama constante de tiempo, que está dada por el valor de la inductancia y la resistencia. Juntas multiplicadas hacen una constante de tiempo e indican en cuánto tiempo se va a descargar esto. Luego acuérdense que el tiempo es el inverso de la frecuencia. Entonces, si tarda poco tiempo, seguramente va a responder a altas frecuencias.
Profile down to zero. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. By the way, we've covered electrical current in detail in a previous video. Do check that out, links down below. What do inductors look like? Inductors in circuit boards will look something like this. Basically, just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers, and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously, we also use them for transformers, motors, and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer. And obviously, we also use them for transformers, motors, and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry.
It says here, but it passes very fast. 1 Henry equals to 1 volt of electromotive force across the inductor with 1 ampere of current per second. A ver si es aquí.
Henry with a capital H. The larger
it was missing there. With, o sea, estaba incompleta esa descripción. Cambia con un ampere. Un Henry es la impedancia, o sea, que produce un volt por cada cambio de un ampere por segundo. Aquí es, digamos, un poco de los parámetros de una bobina, el diámetro del loop con el cual se puede sacar el área, la cantidad de vueltas, su longitud y el tipo que va a estar definido cuando nos va a dar el valor de mu de la permitividad.
The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build, and the back EMF will take longer to overcome. You can't measure inductance with a standard multimeter, although you can get some models with this function built in, but it won't give you the most accurate results. That might be okay for you, it depends what you're using it for. To measure inductance accurately, we need to use an RLC meter. We simply connect the inductor to the unit and it will run a quick test to measure the values. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and
Okay. Did you understand the operation of the coil, of the inductance? Who can explain the operation with let me show. Well, who wants to explain the operation of the inductor? We'll erase. You can have here that's the inductor. Then we will have here the battery. Right? Oh, who can explain me? Imagine that we had a switch here. But in this instant, we close the switch and it becomes like this. In that very instant, it will start a current, but I will show. It will start a flow of electrons in this direction. But that is a change in current because it was zero. And then there starts to be a change in current. So it will find a great opposition to go to the coil's uh, path, and so the electrons will continue here but after a time, they will be diminishing this resistance, and this will become like a plain copper uh, wire which will have no resistance. So these electrons come here, and it will be easier to come through the inductance here. So for direct current, the uh, the inductor opposes a very little resistance, only at the beginning, only in the moment of a change of current. But once there's a steady current, they will be in this direction, and this will be uh, this current here will stop. But if we now open the switch again, that is, we disconnect the battery, there was a magnetic flow stored here, with only one line. So this will continue. And remember that we have this in this direction. Now it will come in this direction, in the opposite direction. There will be another, I will put in blue. Cannot go here because it is open. So it will go here. But this goes here because it has a electromotive force induced. The induced electromotive force I will represent as another battery that will go in this direction. So goes here. But actually, I will put uh, it will be a current that is opposing the original current. So that is this formula. How to obtain this? This is BL. Voy a poner así. This is BL here. The voltage across the inductor is opposite direction. The inductance value is a constant of proportionality and has to do with the change of current over the time. Okay? Okay, any comments? We have finished the time, but I still want to check for the list to see if somebody show up. Zúñiga Mora, he did not come. Vargas Serna Valeria.